my name is Xiaohe Yang. This is my presentation for Computer Science 590. My project is SHAP in machine learning models. I will first introduce machine learning interpretability. I think it's an interesting topic because a single metric is an incomplete description of the situation, and there are many reasons why we cannot just trust the model. For example, like curiosity, model bias, etc. And I will also introduce model-independent explanation methods a little bit. There is feature importance, global surrogate, local surrogate. Local surrogate refers to we train a local model to explain the target model on an independent prediction. And we also have Shapley values, which is a focus for my project here. It refers to a prediction can be explained by assuming that each feature value of the instance is a player in the game, where the prediction is a payout. And the Shapley values can tell us how to fairly distribute the payout among the features. So this distribution can tell us how much each feature contributes to the payout. So that can be viewed as the feature importance. And the SHAP package, which is the sharply additive explanations, combine the Shapley values with local surrogate. And it also uses additive Shapley values to do global interpretation. It also has a great improvement in efficiency. Before, we need to calculate the Shapley values exactly, which takes 2 to the k coalitions for each feature. And right now, with the fastest one being tree sharp, it only takes d squared time complexity, where d is the tree depth. For my project, I will study SHAP interpretability, and I have the 3 datasets I listed here, and I will use 3 metrics, that is feature importance, SHAP, and Lime. And I will also produce different accuracy models. And I pick XGBoost algorithm to use the most, which refers to the gradient boosted decision tree, because the algorithm is very accurate, and the tree sharp is the fastest in sharp. So I want to take the advantage of these 2 points. Let me run through the partial results I have right now. The first data set is an epidemiologic follow-up study that has 7,000 data points. And the regression output is the mortality rate. And the features are the 20 features listed here. And with the first XGBoost model, I got an accuracy of 0.8. And the accuracy is calculated by pairwise comparison of the mortality rate. We want to produce which person's mortality rate is higher. As we can see, the sharp and feature importance, they are kind of agreeing on age is the most important factor, but have some discrepancy on the other characters. Here I also have another model that I only use 100 data points, that is 0.5. And I need to know that 0.5 is not better than a random guess, because we're predicting for each pair which one is higher in mortality. We still have a discrepancy between sharp and feature importance. Yeah, I think there are already papers already explaining this, and they're saying sharp value is always fair, so the other 2 metrics are mistaken. I still need to look more into that. And the other data set I'm having is a bigger one than the previous one. That is a California housing. And the accuracy metrics is square error explained. And my accuracy is 0.8 in the first model. This time we also have the discrepancy, but I think there's a bias in the model, because when I want to plot 14,000 data points to the sharp summary plots, it's really, really slow, and my kernel crashed. So I end up using a subset of the data. I'm worried about it's not representing the whole model. I also have a smaller one using only 100 data points, and they're kind of not agreeing with each other as well. And for the Lime model I have on the bottom, I always just pick a random test point and explain that prediction. The third data set I use is the iris flower characteristic classification dataset. This one is a rather small one with only 150 data points. And even with the depth 1 decision tree model, we can reach accuracy of 1.0. And this time we can see feature importance and SHAP, they're having exactly the same ordering of feature importance. And my random pick of data point for Lyme also have very similar results. For my future work of the project, I plan for this week to do read the implementation to try to fix the very slow graphing plotting for summary plot, and maybe repeat the experiment for images and neural nets to make use of the resources. And my insights for potential future work is that machine learning will be as a service to everyone with or without programming skills. And there will be automated model training. So that's why interpretability is very important. And instead of analyzing the data, we will be analyzing the model in the future. And that's all of my presentation. Thank you for listening.